Hi, everybody. Hope everybody is having a good Wednesday. I'm gonna wind the music down here. Oh, what do we got on the agenda? Something is due tonight, it looks like. Lab worksheet number 1, due tonight. Make sure you get that in by the deadline. Tonight is a soft deadline. Tomorrow is the cutoff. It will close tomorrow. And then it will be unavailable unless you use the NQA coupon. What else do we have? There's a quiz for Chapter 2 that is due next week on Monday. A quiz for Chapter 3 is probably going to go up tonight because we're going to finish Chapter 3 today. And the quizzes start to kind of pile on when we get in the middle here because there's one quiz for each chapter. And some of the chapters are much shorter than others. Chapter 3 is one of the shortest chapters, so that's really all I can think of. So let's get right to it. This is where we left off yesterday, so I'm just going to go to the next slide here. We're going to start today by talking about isotopes. What is an isotope? An isotope is kind of one of those words that you've heard, probably in just some random context, maybe in like a science fiction movie or something like that. I think the most common place that isotopes come up are either in medical imaging, or when people talk about things like carbon-14 dating, or when there's a nuclear disaster. When Fukushima had its meltdown, there was a lot of concern about iodine. I want to say it's 127 or 129 or one of those, or cesium-131 or something like that, because it gets in the water, and then that water got all the way over here because the Pacific Ocean circulates, right? So you hear this word thrown about, but what exactly does the word isotope mean? Is it scary? No, it's a label. There are isotopes all around you. You are eating an isotope of carbon every day. It's carbon-12. It's the most common one. You are breathing in hydrogen and oxygen isotopes all the time. And they're all abundant and common. But what does the word isotope mean? So, what it means is that when you look at a collection of atoms, and you look at their atomic number, but also look at their mass number. So if you have a collection of atoms, or just even a pair of atoms that you're looking at, and they have the same atomic number but different mass number, same Z, different A, then what you are looking at are isotopes. Isotopes are just atoms that differ by the number of neutrons. And a colloquial way to say isotope is just to say, like, oh, I have a specific isotope of carbon. Carbon with 6 neutrons, for example, would be a specific isotope. A different isotope would be carbon with 7 neutrons. So the word is kind of thrown about and misused or misunderstood, but that's how we use it in context in society. But in chemistry, any two atoms are isotopes of one another if they have the same number of protons but different numbers of neutrons. For some reason, these didn't show up at the top there. There we go. Now, lots of isotopes are what are called naturally occurring. So naturally occurring isotopes are isotopes that exist in nature. You could go out and find them. If you had a shovel and you dug into the ground, and then you examined what was in the contents of the dirt that you dug up, you would find lots of different isotopes of carbon and silicon and oxygen and aluminum, and maybe even some of more rare elements. Like, you could probably dig up a pile of dirt, and in every shovelful, you'd find at least one atom of platinum or one atom of gold. Of course you would, because they're like atoms are so tiny, right? You probably find trillions of them, just not enough to really be able to see or use. But all of those things exist right now. And if you examined how many neutrons they had, you would find a naturally occurring isotope. On the screen here, I have carbon-12. Carbon-12 is the naturally occurring isotope that is most abundant for carbon. Carbon-14, on the other hand, is very, 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 very trace in the environment. And the reason for that is because it's constantly being produced by the bombardment of not solar particles, I should say. Just particles that originate from the sun produce this when they pass through the magnetosphere and hit the Earth or hit CO2 in the atmosphere, stuff like that. So you make carbon-14. We'll talk a little bit about carbon-14 in a second. So it is also a naturally occurring isotope because we observe it. But what about something that's like super radioactive? For example, if you look on the periodic table, and I'll get the periodic table link for you real quick. I think I still have that. There it is. Oops, that's my suspended link. You don't want that. There you go. If you look at the element in box 43, element 43 is called technetium. And interestingly enough, there is no technetium on Earth. Absolutely zero. And the reason for this is because every isotope of technetium is unstable. It tends to be radioactive and not last very long, for whatever reason. That's just how it is. That's just how technetium behaves. There's another element that does that too, called promethium. It's number 61. And so those isotopes can't be found. In order to find them and put them on the periodic table or to use them or for whatever, we use technetium in medical imaging. What we have to do is we have to make it. And so that makes it a synthetic isotope. Synthetic isotopes exist for a while, but usually not long enough to exist in nature for any appreciable amount of time. Now, nature has been around for a very long time. How old is the Earth? It's billions of years old, right? So for something to be naturally occurring, it would have to have appeared and then been part of the Earth's formation when it started. Then, billions of years later, you get to today and you dig it up, and if it's still there, it's a naturally occurring isotope. Not all isotopes can do that. For example, the isotope on the left, carbon-12, is essentially so stable that we don't know its half-life. It will stick around for virtually forever. This one over here, though, has a half-life of about 7,000 years. I think it's like 6,930 or something like that. And what that means is that every 7,000 years, half of our sample will decay. We're actually going to explore that in a later lab when we discuss radioactivity. For something to be synthetic and not naturally occurring, its half-life needs to be relatively short. So 7,000 years is actually pretty relatively short. However, it's constantly being made and we can observe it. And so this is where carbon-14 dating actually comes in, is carbon-14 is abundant enough in the environment that it ends up in plant matter at a pretty constant amount. And that constant amount is very, very, very small. But what ends up happening, we'll go to this chart here to show this. What ends up happening is that, say you have your carbon-14 and it's in a leaf or something. So here's my leaf. Here's the little stem. And some parts of that have carbon-14 in it. Just small amounts. Now, if you're a dinosaur, here's my dinosaur here. Here's his tail. And he's got... We'll just do this. There's his foot. He's taking a step, you see. He's a big stompy guy. So here he is, and he's going to eat the leaves because that's what they do. So they eat leaves off of trees. Here's my tree. And in those leaves is a small amount of carbon-14. Now, that carbon-14 will pass through the dinosaur and become part of the dinosaur, but most of it does pass out of the dinosaur as waste, right? Because it's fiber. It's insoluble fiber that comes through in some parts of it. But the amount of carbon-14 that is in the dinosaur should be roughly constant while the dinosaur is alive, because any carbon-14 that is coming out of the dinosaur is being replaced by new carbon-14 that the dinosaur is eating. And so there's a rough amount that is constant in the dinosaur's body. Now, when the dinosaur dies, this is going to be kind of sad because here he is dead. Oh, I guess it'd be more like that. There we go. So when the dinosaur is dead, whatever carbon-14 was in the dinosaur at the time of its death remains there. But over time, some of it irradiates away. Boop, boop, boop. And so every 7,000 years that pass, half of the carbon-14 that was in there decays. And so this is called a half-life. Now, if we dig up the dinosaur and then test its bones later on, we could observe that, like, oh, there is some amount of carbon-14 in there. Maybe we would discover, oh, this is how much carbon-14 it has today. Well, if we follow this pattern, we could then say, okay, well, 7,000 years ago, it would have had twice as much. And 7,000 years ago, it would have had twice as much. And so on and so forth. And what we can do is we can then just extrapolate back to however much it should have had, because we could say that other creatures that are roughly the same mass should have this much. And we can then age it. So this is the premise by which carbon-14 dating works. Now, I'm using a dinosaur and I'm using carbon-14, and dinosaurs were 65 million or so years ago. That's a lot of geological strata that have gone by since then. So carbon-14 dating for dinosaurs, probably not super reliable because the half-life is just too short. There are other half-lives out there that can be used, but the premise remains the same. Generally speaking, if you have, like, maybe between 1 and 10 half-lives of time, so, like, up to 70,000 years for carbon-14, this would be quite accurate. But as you get further and further and further and further back, there's probably a little bit of error that propagates and gets bigger and bigger as you go further back. But there you go. I hope you appreciated my drawings. They turned out way better than I expected them to. I'm not really an artist, so we'll remember our dinosaur as he was alive when he was eating leaves. So that's just some of the cool stuff that we can do with half-lives. What was the answer to the question? Oh, Brittany's question. Okay. The lab is due tonight. That is a soft deadline. The hard deadline is tomorrow. It will close at midnight tomorrow. I should say 11:59 tomorrow on Thursday. Now, when we're working with atoms individually, we are working with very, 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 very tiny masses, and that's obnoxious. We don't want to deal with tiny numbers because writing this number down over and over and over again is going to be really frustrating. No problem. Happy to help. So what we have done is we have created a sort of unit that helps describe this. So what we're going to do is we're going to say, okay, the number of protons and neutrons inside an atom is going to be this unit for us. We're going to call it atomic mass units. And so for our purposes, we're just going to say, okay, every time there's a proton or a neutron, that's 1 AMU. So we would say, okay, carbon 12, instead of weighing this many grams, would be 12 AMU. And boron 10 would be 10 AMU. And chlorine 35 would be 35 AMU. And so we're just going to take whatever the mass number is and make that the mass. Now, because this is a super introductory class, that's good enough for our purposes. In reality, the numbers don't quite work out this well. For instance, a proton is actually very, very, very slightly more than 1 AMU, and a neutron is very, very slightly more than a proton. But since we're not an analytical class and we just want to figure out an estimate anyway, this will work for us. So just for our purposes, remember that the mass number A is going to be the atom's mass in atomic mass units, because that's going to be relevant in a little bit, and then also again at the start of chapter 6, which will be coming up pretty soon, actually. A lot sooner than you think. Now, this is the actual definition of how AMU work. Carbon 12 is exactly 12 AMU, and then we use this to weigh other things using a device called a mass spectrometer. And the way that works is we basically catapult atoms through this device, and then they hit a detector based on their mass. And the higher their mass is, the more force we need to apply to them so that we get it to hit the detector. And so we can calibrate, oh, this much force in the detector equals this much mass. So for instance, boron 10 hits the detector when you put it through a field that is 0.83442 times as strong as that for carbon 12. And so its mass must be this or that. You could see that boron 10, which we would predict would be, oh, it's 10 AMU based on the shortcut Wes told us. Here's its actual mass, and you can see, oh yeah, that's close enough. We don't care about those last digits in 121. This is 161, i.e., if you were here 2 hours ago for my other students, then yeah, we absolutely care about those digits. But here in 121, whatever. 10 is good enough. Now, why do we care? Because I'm going to take those numbers, those average, or these masses that we've calculated, and we're going to get some information off of, or from, this to create numbers on the periodic table. And the way that this works is that we say, okay, well, if boron 10 weighs this, and like say boron 11 weighs this, and like I could just scribble these out. We're just going to do this. What would the average be if I just took a random sample of boron? And you might think, oh, well, it'd be 10.5, right? Because that's the average of 10 and 11. But that's only true if we have the same amount of boron 10 and the same amount of boron 11. If I have lots of boron 10, but very little boron 11, then this average is going to get pushed over in this direction, right? And so what we need to do is we need to take what's called the weighted average. And so the weighted average just considers the percent abundance. And what I'm going to do is I'm going to show you the calculation to do one weighted average, and then you're not really going to have to worry about it anymore. So we're going to look at bromine. What would the weight of bromine be? So here's bromine 79. It would be 79 AMU, and this would be 81. Now, if it's 50-50, we should do something like this. 50% times bromine 79's mass, and 50% times bromine 81's mass. And when I do that, I get 0.5 times 79 plus 0.5 times 81, and I get 80 as my result. And now if you look at the periodic table for bromine, you will notice that the mass number underneath bromine is 79.904. That's real close to 80, right? So for our approximation, that's good enough. And when we do this calculation and get this number appears on the periodic table. This is called the atomic mass. And it's on the periodic table. So the atomic mass is for the average mass. Now let's do the average mass for something where there isn't 100 or 50-50. Actually, I'm going to leave that practice example for you. I'm going to pick a different one. But I got to look it up real quick. So let me look up isotopes of something. Isotopes of... let's do chlorine. No, let's not do chlorine, because that's also coming up an example. Let's do... let's just do carbon. Let me get the percentages here. 98.9 and 1.1. Okay. Oh, there's Dinosaur Friend. I don't want to delete him, but... Oh, there it goes. Alright, so we've got carbon 12 and carbon 13. So carbon 12 weighs 12. Carbon 13 weighs 13. And according to the internet, 98.9% of all carbon is carbon 12 and 1.1% is carbon 13. Now, carbon 14 is less than 0.1%. That's what trace meant when I wrote that earlier. So I would do the weighted average. I would say, okay, so 98.9% times 12 plus 1.1% times 13. And this would all be an AMU. So let's do that. 98.9% times 12. So that's 11.868. And I'm going to just play fast and loose with the sig figs here because we're just estimating anyway. Oops, 0.011 times 13. And when I add these two numbers together, you get this. And if you look on the periodic table, what do you notice? You notice, wow, that's real darn close to what it is on the periodic table. And yeah, it totally is. Now, I'm cheating here because I didn't do sig fig, so this number would actually stop right about here. So we would only get these for our answer. But just to show you as a proof of principle, this is how the mass number is calculated on the periodic table. Is you just do the percent of the first one times its mass and the percent of the second one times its mass. And you can keep doing this over and over and over again until you have got all of the isotopes. Now, if I have a mass of 12.011 as my average, and I asked you instead to consider it this way, which of these is there more of? So which is more abundant? How would you calculate that? Well, you don't have to actually calculate it. You just look at the number, right? What number is this closer to? Well, it's definitely closer to 12, right? So carbon 12 must be more abundant than carbon 13 because the atomic mass, which is the average, is also closer to that number. So if you're looking at the periodic table, you can usually predict the most abundant isotope. And I say that because it doesn't always work. With bromine, it doesn't work. There actually is no bromine 80. 79 and 81 are just equally abundant. That's nature's way of saying, haha, sucker. Can't follow this pattern, but for almost every other isotope, this works. So you can at least make that prediction. All right, so I have a bunch of questions here. So the first one, I want you to try and do the calculation here. So we've discovered the newly unidentified atom X, and 20% of this is this isotope right here, and 80% of it is this isotope here. Well, what its atomic mass be on this periodic table? And then the second question I have here is, here's chlorine's atomic mass. There are only 2 isotopes. Which one is more abundant, 35 or 36? And then tell me what percent of atoms would have that mass, shown below. Now, be very careful. Think about what the mass of atoms is and what we've discussed here. So type your answers in the chat, and we'll go over the answers together in just a second. Say hi. Meow. Meow. Maya says hi. One more minute, we'll go over the answers here. All right, so let's go over here. Oops, that's not going to super help me. And I will apparently do nothing. There we go. Okay. All right, so if I want to calculate the average mass of this atom, so the first isotope of X has a mass of 43, because that's its mass number, and we'll times that by 20%. And then the other one's 80% times 44. Now, we know how to input this number, right? 20% is just 0.2, yeah? And that's 0.8. And so when I type all this in here, I get, the first one I get 8.6, and this one I get 43.8. So when I add those together, I get, oops, sorry, hold on, that's not right. That's the answer I get. And so there we go. So because X44 is much more abundant, the atomic mass is closer to 44 than it is to 43. All right, for the second one, if the atomic mass of chlorine is 35.453, which one is there going to be more of? Well, there's going to be more of the one that is closer to this number, and so that's 35. Now, is there going to be much more? Not much more. Just enough to pull the average towards it. Now, the second question, what percentage of atoms have a mass of exactly 35.453 AMU? And the answer is none. No atoms have a mass of exactly 35.453. The atoms only have 35 or 36, right? So no atoms weigh 35.453 because This is not the mass of any given atom. This is the average. So the number on the periodic table does not represent the mass of any given atom. So be careful about that. That's the mass of the average. Now, how do you know you are getting an accurate average? Well, you would have to weigh a lot of atoms, right? As you weigh more atoms, excuse me, your accuracy goes up because you are more likely to have a representative sample. Well, thankfully, atoms are really, really tiny. So if you take 20 trillion atoms, you're probably getting a representative sample. And so if you take those on average, the average atom in that 20 million sample, or 20 trillion sample, would weigh 35.453 AMU. But any individual atom would not weigh that. They would weigh either 35 or 36. All right. I hope that discussion has helped clarify some of the uses of the term isotope and where some of the numbers on the periodic table come from. As you probably could tell, this whole chapter is basically just what are atoms and how do we get this information onto the periodic table. So that's where the next section is. It's just what other information is on the periodic table. What can we do with it? So let's talk about the periodic table a little bit. Somebody a long time ago realized that if they looked at very specific elements, they had very similar reactions. Now, I don't know if we've done this because I'm teaching 3 introductory classes and they're all different. But one of the things that was shown, or one of the things I've shown in other classes, but I may not have shown it in this class, is the reaction of sodium and water. We're going to take sodium metal, and we're going to drop it into water. And so first I need to, you know what, actually I want to get a second video of this real quick. I'm trying to find one that doesn't look like it's going to get me copyright struck. Also one that like is short enough that I can put it in here. Oh, actually this might be okay. Hold on. Sorry, I turned the sound on. I'm just clicking through the I'm tabbing through this video here. Let's see here. Okay, yeah, this is the one that I want to show. Okay. Okay. So let me capture this. Sorry, I have a different video that I want to show you. But I wanted to show you something else first. And then I found this one, which I have seen before, and this is actually a good one. Alright, so what we're going to do is we're going to put alkali metals into water. Now, I've sort of told you the trick here, but that's okay. So let's watch what happens here when we drop these in water.
Of the alkali metals, the reaction with water. We'll start with lithium.
This is what lithium does when you put it in water.
The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction.
So, don't worry about the equation.
Gas is produced,
but you'll see that the metal is just sort of like zipping around.
With a single.
I'll just turn him down here. You can see that the metal is just zipping around. Here's potassium. Now it's catching on fire.
By the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time,
rubidium just explodes very violently.
From the reaction. You can see that things gradually become more terrifying as we go down the group.
And then I'm going to let cesium speak for itself.
Alkali metal.
Whoops. Oops, and I clicked on something randomly there.
There are 6
Okay. And that's the beginning of the video, so we're just chopping pieces of the metal to put in the water. So, as you saw, there was definitely a trend there, and that trend was water plus alkali metal causes a reaction. And as we went down the periodic table, the elements got more and more and more reactive. And so now I'm going to show you the other video that I have here. So you can see those in terms of speed. It's a little more obvious when you're looking at something small scale. So it's just not as fun to see that last, unless you get to see that last bit explode there. So this is going to be sodium. We don't need to look at lithium because it's just slow. So here comes sodium. There it is in water. And so you can see that, okay, sodium goes pop. It dissolves in the water and then vigorously starts to burn in an orange flame. Now I got to get the other elements up here, but I need to actually go into another window to do that, so hold on. So I want this one. Oops, I started the reaction on accident. And I want this one. And I want this one. You can hear the videos because I'm not clicking on them fast enough. There we go. All right, so here's potassium again in water. So remember what sodium looked like, and then compare it to potassium. Would you say that they're similar? Or different? And then we'll get rubidium here, and you can see pretty similar. But you can see that these are getting faster and faster and faster, like the other video showed you. That was rubidium in slow motion there. And then here's cesium. Cesium is so fast that we have to show it in slow motion, because there it's done. Here it is in slow motion. Which is just fun. And then there's the still frame of it exploding. Alright, so you will notice that, now that I'm going to go back to here, the elements that we chose to examine for that experiment are these right here. All along the left here. And it turns out that that is not by design. Now, the periodic table, or sorry, not by design. That's not just coincidence. It is by design. I misspoke. So, we have created the periodic table to resemble the properties of things that we examine out in nature. And one of those properties that we just looked at was alkali metals in water. Now, before they were called alkali metals, they were just whatever random elements they were. We threw them in water, and some of them exploded, and some of them didn't. So, what we decided as, when I say we, I mean the royal we, civilization, we decided that we were going to align anything that had a similar reactivity into a column. And so, for example, all the elements in column 1 react violently with water. All the elements in column 2 fizz with water but don't react very violently. Elements in column 3 are stable. Elements in column 7 do something, and so on and so forth. There's a myriad possibilities that we can explore, not just with water. Like, we could use hydrochloric acid, we could use gasoline, we could use sugar, we could use sulfuric acid, we could use hydrogen peroxide, all different compounds that we want to throw in there. And we can test this for all the things. And what we find is that arranging the periodic table in this manner, we get a predictive power. And so that's really useful. So the takeaway from this little video is that elements in the same column behave similarly because we put those elements in those columns. One particular property is that elements in the very far column on the right, the noble gases, if you have p-table open still, those elements are inert. They don't really react with anything. And they just kind of hang out. That's a property of those substances. So we threw them all in that last column. That's the noble gases. Now, in all of this we that I've been saying, really, we could point the finger at this guy. This is Dmitry Mendeleev. He did all the hard work. Dmitry Mendeleev was a famous chemist in the late 1800s who was the first to probably definitively quantify these ideas and arrange them into a periodic table. And so he produced an early periodic table, which had 8 groups in it. We have since changed the periodic table a little bit to accommodate for more elements. But his deductions about the nature of matter and how it behaves helped us formulate this idea that, oh, elements have specific properties, and those properties are governed by some feature about them. And there are some features that are similar between atoms. And that has to do with electronic structure, which we're going to unfortunately skip over for the most part. We'll talk about it very briefly at the beginning of Chapter 4. But suffice it to say that sodium and potassium and rubidium have something in common, so we can put them in the same column. In fact, this was so powerful of a predicting tool that at the time when Dmitry Mendeleev was creating it, there were blank spaces in this periodic table. And he said, you know what? I bet there's an element out there that it looks like this. It has these properties. It will react similarly to this and this and this. And here's its density and so on and so forth. And he was able to identify atoms that had never been discovered yet. And so people went looking for them, and sure enough, there they were. So I believe gallium, element number, is that 31? Yeah, 31. Gallium was discovered this way, or germanium, one of the two, I believe. Now, there are over 110 elements in this class, and bad news, you do need to start memorizing. No, I'm just kidding. We have this table out here for this entire reason, so what I want you to do, instead of memorizing the periodic table, is I want you to bookmark p-table, and then before every quiz, open the bookmark for p-table and have it handy. Remember, I don't lock down your browser. I don't give a shit about any of that. You use any resource you want. Have the bookmark for p-table handy. And it's right here. You can see it in the chat. Right there it is. So go click on this. Like, do it now. Do it now. Do it. Yeah, you know you want to. All right. So that'll get you a periodic table that has all 118 elements on it. You do not need to memorize them. That's just a joke. But what you do need to do is you need to be familiar with any pairs of elements that are intended to confuse you. And when I say intended, I mean I will pick them just to make sure you're okay. Another common issue... Oops, I didn't mean to do that. Another common issue would be titanium versus tin. Where's tin? Well, it's not this. That's titanium. Tin is right here. Notice how I'm always circling one with a funky symbol on it. And the funky symbols are due to things like Latin. So, like, the Latin elements have, like, iron is Fe. There isn't an F in iron. I don't know how many of you spell it iron, but it doesn't exist in it. But it did to the Romans who spoke Latin. It was called ferrum for them. Other issues that come up, anything that has a C in it. There are so many elements that have C's. So like chromium, cobalt, copper, carbon, chlorine, cesium, calcium, cerium. There are just so many C elements there. Be really careful about anything with starting with a C, that you are actually getting the right one. I did not get a notification that said my stream went down. I'm not dropping any frames, so it's definitely not my end. It could be YouTube. Try hitting refresh. You might not actually be able to hear me, I realize, because your stream might be down. Try refreshing the page, and it hopefully will work. Sorry, I realize I might be just talking to the void for you. Something you can do is if your page starts to slow down or like it gets weird, so I can actually show you this. So over here, this is what I'm seeing for my stream. So you can see that like my stream is currently caught on the start. You can click this button that says live right here. Skip ahead to live. It's hard to see that really. So there we go. So now it's caught up. But if I click on this where it says live, you can see that I'm actually like 2 minutes behind on my view here. So click live and it will update to immediately what I'm doing, which you can see now in the screen there. So if you're ever like behind, you can either refresh or you can just click on the word live and it should push you back up to the front. All right. Are we about break time? Yeah, we are about break time. So let's take a break. I'll put this on the screen here. Can I repeat what I said before I circled this element? Sure, we can go back to that. We'll do that before we do the break here. So what I was talking about when I was circling these elements, and I was circling them based on color here. So the ones in blue here are commonly mistaken for one another. So, for example, potassium is not P, that's phosphorus. Potassium is actually K. Tin is not Ti, that's titanium. Tin is actually Sn. So there are pairs of elements on the periodic table that you need to be just careful of. Don't mistakenly say, oh, S is scandium, because that's sulfur. There are so many elements that start with C. That was why I was circling them all. If I ask you which one's calcium, like, or which one's chlorine, well, there's an H in chlorine, but there's no element with CH out there. So that could be confusing. Is it CO? Is it CR? Is it CL? It's CL, it turns out. So just be kind of aware. Look at the periodic table carefully before you select an element. Because you'll always be able to use p-table, the names will always be given to you. So don't just like assume that you know an element if you aren't sure. That's really all I had to say about that. All right, so when we come back, we will talk a little bit more about how we categorize different parts of the periodic table. So like going up and down. Oops, hold on. I hit a button and it started making music. We'll talk about like how we categorize like the columns up and down, the rows left and right, give some different names for different places on the periodic table, and also some other general descriptors. So we'll look forward to that when we come back. So I will see you in about 10 minutes. 10 minutes in a row, 2 times in a row. All right. I just saw your question. If you have questions about sig figs, definitely email me, or type in the Discord chat. We're not gonna have time to go over that today, unfortunately. There will also be a review session in week 5, so that would be good then too. But that's 2 weeks away. So obviously, if you have a question that you'd like answered about earlier stuff, send me an email. That'll be a better opportunity for me to answer it. All right, so what we're going to do now is we're going to take our periodic table, which I just had, and now I've clicked off onto some other thing here. There we go. That's not the periodic table. There we go. Boop. There's our... well, there's our periodic table, everybody. I hope you enjoyed it. And now it's gone. What have I done? What have I done? Now it's upside down. Oh, no. Oh, no. Okay, hold on. I've done a terrible thing here. Let me fix it. So here's our periodic table. And you can't see the whole thing on the bottom because I got to actually go over here and scroll it up and down. All right. So we're going to define some names for things on the periodic table here. And so the first ones we're going to talk about are called groups. A group is a column on the periodic table. So for example, this would be a group right here. This is group 18 because the number 18 is at the top here. This would be group 1. This would be group 7, and so on and so forth. So we're going to number groups based on what number is at the top. Now, there are 2 numbering schemes for groups. There's one that just numbers them left to right, 1 to 18. There is a second numbering scheme. Sorry, not numbering scheme. There is a second numbering scheme that splits the groups up into 1 through 8, A and B. That's the sort of Mendeleev numbering scheme that you might see on different periodic tables. We can use both. I'm just going to stick to this one right here, although my slides are going to refer to 1 through 8A, so don't worry about it too much. The A group is these 2 columns on the left, and then these 6 on the right. Those are groups. Groups are columns going up and down. Note that all of these elements down here are not in any column. They actually kind of go here, but also not really. So if I ask you for the group number of any element down here, these don't have a group number, these 2 rows at the bottom. We'll talk about what those are in a second. Going across the periodic table from left to right are called periods. So this is period 3, from sodium all the way to argon. Period 4 would be from potassium all the way to krypton. And we call it the periodic table because patterns appear periodically. Every time you go to the next period, all of the patterns appear again. So that would be the element in the first column reacts violently with water. This element reacts mildly with water. This element over here is inert, that sort of thing. So you see the patterns reemerge over and over and over. So those are columns and groups. Columns are groups, rows are periods. And so my slides are talking about this, but I feel like it's better to just like give you the visual example. And then we don't even need this picture anymore because I have this picture. I'm just going to click on them and you can see which ones are which. So the first column we're going to care about is the alkali metals. So that's these guys right here. Elements in the first column are considered to be alkali metals, and all that really means is that they are metals that are alkaline. When you add them to water, you create a basic or alkaline solution. We're going to talk about acids and bases in chapter 10. So you don't need to know what alkaline means, but that's where the word comes from, is acids and bases. And these elements make bases when you add them to water. The elements in column 2 also do that, but they're slower and they're less reactive. So these are the alkaline earth metals. They're just differentiated in that way. I'm going to skip all the way to the other side here. These are the noble gases. The noble gases, like all nobility, do nothing. They just sit around all day. They twiddle their thumbs. They don't react with any other chemicals. In fact, they just bounce around and they're inert. You could breathe argon and be perfectly safe. It would not hurt you in any way, other than the fact that you would slowly asphyxiate because you would you would not have oxygen access while breathing argon. But the argon itself would not hurt you. Same with krypton or xenon or whatever. In fact, the only thing those things do is they lower your voice because their density is higher. And so when you talk, you start to sound like this. And if you go the other way and breathe in like helium, everybody knows what the helium voice sounds like, right? You sound like this. You sound like a really high voice. I can't go any higher. I used to be able to go a lot higher, but I hit puberty at 35 or something. I don't know. What other elements do we have here? We have the halogens. The halogens are this column. Unfortunately, I don't have a button for halogens here. But the halogens are this column here. It's group 17. Group 17 are the halogens, and they're common enough that it's worth knowing them. So you might have heard of like a halogen lamp. A halogen lamp is a lamp that contains chlorine in it. And when you pass a current through it, you get a very bright light. I'm trying to think of other places where you've heard of like halogenated stuff. And like I'm thinking of like flame retardants. So halogenated flame retardants often contain bromine. So if you live in California, this is a big thing. They put this compound, this brominated compound, into a lot of fabric so that when it burns, the burning process goes slower, and the flame could go out. So it slows down the spread of fire. Those are the only columns that I really care about. The other stuff that I care about is, so these in the middle here, these are called the transition metals. Transition metals are important to chemists. In an allied health setting, really the transition metals that you're going to care about the most are things like iron. So iron is important if you are trying to avoid being anemic. If you don't have enough iron, it's hard to carry oxygen through your body because that's the main transport. Is iron is part of the hemoglobin protein. And without the iron as the binding site, you can't get oxygen to where it needs to go. Other elements that are important, I think, I don't know my biology super well. Iron is very important. The other ones are trace elements. Why is it Fe? So Fe is the Latin name for iron. I'm going to type it in the chat here. So its Latin name is ferrum. So there it is right there. And the first two letters of ferrum are Fe. And we just use Fe because, well, they found it first. And now it's tradition. Like we've just had it like this for so long. Be careful about this because IR is actually on the periodic table. It's right here. This is iridium. So don't accidentally take iridium when you're trying to look for iron. The other two that I want to mention are the lanthanides and the actinides. These are these two columns right here. And the only reason that I care about these is because I personally did research on lanthanides and actinides. The lanthanoids start with lanthanum, and they go right here, and they sort of have their own little part of the periodic table. They're their own row. There are reasons for that have to do with electronic structure, but we're not really going to discuss them in the class, unfortunately, because we just don't have time. And then the actinides start with actinium here, too, and they have their own row. I worked in a lab that was specifically lanthanides, and so, of course, the element that they stuck me with is uranium. So I've done a lot of chemistry with uranium. I'm actually a uranium expert, which is weird to say, right? I probably shouldn't say that live on the air on a public broadcasting of my lecture. That I know a lot about uranium. It's mostly just like boring chemistry. Like I have a paper published where I did a reaction with like methyl lithium and uranium dicyclopentyl chloride or something. I don't know. That was 20 years ago. I don't remember. It's not important. What's important is that these are actinides and these are lanthanides. That's what I want you to know. Other than that, we're going to get to metals and nonmetals in just a second. So I'll save that for when we get there. But that's the next part. So what I want you to do now is I want you to go through the periodic table that I just showed you. And I want you to find these elements, and I want you to give them a name, period, and group number. And then give me a category that describes them. So I've only listed a few of the categories here, but for example, like if I asked you to go find gold, oh, I do ask you to find gold. If I asked you to find, I don't know, titanium, we'll say. Let me make sure that you don't have to find that one too. Okay, good. So if I asked you to find titanium, so what you would do is you would say, okay, where's titanium? There it is. So this is in group 4, period 4. It's called titanium, and it is a transition metal because there you go. Okay, so do that with all of the elements that are shown on this slide. Oops, I hit the wrong button. There we go. And we'll go over the answers in just a second. One or two more minutes, and we'll go over the answers. All right, let's go over the answers here. So I'm going to just pop this up on the screen here. So the first one that we want is astatine. So that's right here. So that's group 17, period 6. And the best label that we can give for that would be halogen. Now, unfortunately, I can't write all this down because if I write somewhere, it'll move the cursor around and all sorts of crazy shit happen. Well, actually, now that I'm looking at it, it's not actually moving the cursor, so I can write this down. Okay, so astatine is group 6. Oops, not group 6. I'm sorry, period 6. Group 17, and is a halogen. There we go. All right, what's the next one that we've got here? I lost that thing. There we go. So now we've got potassium. So that's over here. So potassium is period. I'm writing this on the slide, which you can't see, but I'll remove the screen in just a second. Period 4, group 1, and that's an alkali metal. And then gold over here. Gold is period 6. And it's in group 11. And it's a transition metal. And then we've got rhodium, which is group period 5. Group, I want to say 9 or 8. 8, yeah. And it's also a transition metal. And then finally tellurium, way over here. Oops. There we go. Tellurium is period 5. Group 16. And it doesn't really have a good label to give it. So we just won't give it one. All right. There you go. There's my answers for that. So you can see those. You can pause the video if you need to copy those down. Oh, and there's the homework practice. So if you want to copy that down too. So. All right. The last little bit, chapter 4 or chapter 3 that we're going to do. We're going to talk about metals and nonmetals. Where are metals and nonmetals on the periodic table? Well, first, let's talk about properties that define things as metals. So a metal is going to be defined as rhodium is in group 9. Did I write the wrong number? I can't read columns, apparently. Oh, I clicked on the wrong thing. Yeah, I was doing ruthenium. So yeah, it's group 9. Let me fix that. That's why I said 9 at first. I was like, oh, I think it's 9. And I saw 8. And I was like, oh, okay, maybe it's 8. I was right. I should have believed myself. Okay. Thank you for catching that. All right. We're going to define a metal as anything that has the following properties. And so Bender is on there for a special reason. We'll talk about Bender in a second. So all metals conduct electricity and heat effectively. So what that means is that if you put something on the stove, we would need it to be made of some material that would heat up very quickly. We want it to transfer heat quickly to the food so that we can cook faster. So we make skillets out of things like iron or copper or steel or stuff like that. So metals have high conductivity. We also make wires to transmit electricity across them out of these materials, particularly copper, because copper is very good at conducting electricity. Silver is even better, but silver is expensive. The other property that metals have is that they are what we call malleable or ductile. So if something is malleable, that means that if you hit it with a hammer or you impart a force upon it, it doesn't like crack or break into pieces. It instead just flattens. And so if you do this with a blob of metal, I guess you could say, like a ball, if you hit it enough, it will eventually become a flat sheet. And if you keep hitting that sheet, it will just become more and more. It'll become thinner and thinner and thinner until the sheet is extremely thin and then very large. So this is how aluminum foil is made, is you basically press the aluminum until it is the desired thickness. Ductile means that you can pull on it from one dimension, and it will eventually just become a wire of whatever gauge you need. So copper wire is made this way too. If you pull on a length of copper long enough, it will get thinner and longer, until eventually you just have a really long length of wire that is the dimension that you seek. So all metals can do that. And then the last property of metals is that they're shiny. When you shine light on a metal, the electrons that flow over the surface of the metal are pretty mobile. And so the effect is that the light is reflected in a way that it looks shiny to you. And so anything that has a high degree of luster is something that we consider to be a metal. And that's why Bender's on here, because what does Bender say all the time? Bite my shiny metal ass, right? That tells you that Bender's a metal, because he's one, shiny, and two, he said the word metal, right? Now, what about nonmetals? Nonmetals do not have any of these properties that are listed above. So nonmetals are not shiny. Nonmetals cannot be drawn into wires or sheets, so if you hit them, they tend to shatter. They have low conductivity for heat and also low conductivity for electricity. They're insulators, basically. So iodine, which is shown here, is this purple crystalline substance that if you hit it, just fragments into 1,000 pieces. The same is true if you do this for coal. Coal does not flatten into a square sheet when you hit it. Coal just shatters into a bunch of pieces. You also cannot conduct electricity with charcoal. It is a very good insulator. And lastly, some substances, such as silicon here, have some of these properties, but not all of them. So for our purposes of doing computing, we want something that is sort of conductive, but not super effective at conducting electricity. Because if you had a system where the electrons just flowed uncontrolled, we couldn't move them through, say, logic gates or whatever, and thus we couldn't make a computer. So silicon is really good for that. And the reason it is good for that is because it has some electrical conductivity and some thermal conductivity, and it won't melt super quickly when we use it for that sort of application. All right. There's the homework practice for the metals and non-metal section. I can show you on the periodic table where those are, but I have a better periodic table here, still waiting to be shown. And so I'm going to just show it to you right here. So if I click on metals, there we go. Oops, I didn't mean to bring up a little pop-up there. All of the metals are on the left side of the periodic table. And then all of the non-metals are on the right side of the periodic table. Now, in the middle here, you have this blue region. These are the metalloids. Those are the elements that are sort of metallic properties, sort of non-metallic properties, hard to really classify. Now, on this diagram that I have visible here, you can actually see there's this zigzag line that goes through them. Not all periodic tables have this, unfortunately, but the ones that do, this is useful to see. I'm going to highlight this in like sky blue or something. There we go. Oh, no, I guess we're doing green. That works. This is the metal, non-metal line. And if you touch the non-metal line, non-metal, there we go, line. Anything that touches the metal-non-metal line on an edge is a metalloid. So these are all metalloids. There is one exception. Well, there's two exceptions, but we only really care about this one. This is aluminum, and this is polonium. But polonium is radioactive. So we don't really care about it anyway. That's supposed to be my radioactive symbol. I don't know if that's very accurate. But aluminum we do consider a metal because it doesn't have very many non-metal properties. In fact, it doesn't really have any at all. It's all metallic properties. But everything else that touches that line behaves like a non-metal. And then this guy over here, astatine, this is also radioactive as well. So we don't really care about the bottom part of the periodic table terribly much. All right, that's all we're going to do for Chapter 3. So the rest of this here talks about electron arrangement. You're free to look through this if you want to, but we're not actually going to do it. And as you can see, like, this gets kind of ridiculous with all of the diagrams here. And we're just not going to do that, so... oh, I went past our little dancing orc here, so we'll do that real quick here. Where's my music? There isn't any music. For some reason, it doesn't work. That's okay. All right, so that's Chapter 3. We're going to put the Chapter 3 quiz up after class. I am going to start Chapter 4 because I do think that I can talk a little bit about this in the last... Let's see here. I got like 15 minutes left. That's too much for me to just bail on, so... All right, so I'm going to put this on the screen here. Boop. There we go. All right. The first slide of Chapter 4 has this introduction that talks about polyatomic ions. And in Chapter 4, we're going to be using this list of polyatomic ions. However, it says that you need to memorize it, but this is an online class, so you don't actually have to memorize anything. You just have this reference available. What we're going to start doing is we're going to start using polyatomic ions in various applications throughout the course. And I'm going to be referring to things as like carbonate or phosphate or sulfite or whatever. And so I'm going to provide you with this list here. If you have, I don't know what edition this is. I want to say 7th, but it's on page 106. But I've provided this list for you right here. And so what I want you to do is either commit them to memory or just have it handy when you need to use it. Because these are the common polyatomic ions that you'll encounter in allied health. And I personally think it's worth memorizing these because when you get to biology, when you get to cell bio and stuff like that, they're going to be throwing around like, oh, you need a phosphate buffer. Oh, we make carbonate. Oh, this is the citric acid cycle. And then we do this thing to it. And you're going to see all of these words just pop up all the time. And if you don't know what nitrate is and you have to keep looking it up every time, you don't know what ammonium is and you have to keep looking it up every time, that's going to eat up all of your time. And that's obnoxious. So, excuse me. My advice to you is to try and commit these to memory because that will help you. But I can't force you to do that. It's an online class, so have it handy. Remember that these are on the slide at the start of Chapter 4, and you'll be in good shape. All right. We're going to use those when we get to the very end of this chapter and start naming ionic compounds. Chapter 4 is about ionic compounds. We're going to talk about ions. We're going to talk about why we care about the structure of atoms from Chapter 3 in terms of electrons, and then what was all the stuff that we skipped over at the end of that. How do we condense that down? Because we can actually condense it down to a very, very, very simple idea that completely obviates the need to have done any of the last two sections that we skipped, and that's why I skipped them. All right, so we're going to start by talking about an overview of bonding here in Chapter 4. So let's do that. What exactly is a bond? A bond is any force that holds two atoms together in place. And so what that means is that our atoms will be stuck together to form a unit of some sort. Depending on the type of bond, we're going to call the unit a different name. So it'll either be a formula unit for an ionic compound or a molecule for a covalent compound. But there are different types of bonds that we can get. And we're going to explore 2 of them in this class. So the bonding we're going to look at ionic bonding. This is chapter 4. And then covalent bonding is chapter 5. All bonds involve electrons. And so what that means is that when we form a bond, the electrons of the atoms will interact in some way. With ionic bonding, we're going to be doing one particular technique, and then for covalent bonding, we're going to do something totally different that also works. Okay? So we're going to split this chapter, or we're going to split the next 2 chapters into method A and method B, basically. Now, we have already talked about what an ion is. An ion is any atom that has a different number of electrons than it does protons. So when you make an ionic bond, you have to move electrons from one place to another. So in other words, what happens here is that if I get rid of an electron, this is the result. If I have chlorine and I gain an electron, this is the result. And then what do we say about opposite charges? Well, they attract to each other, right? So that would form an ionic bond. So to make an ionic bond, we need to make an ion. That's the first step. Now, what are some properties of ionic compounds? Ionic compounds tend to have really high melting points relative to other compounds. So for instance, if you have heated up sugar on your stovetop or tried to caramelize something, you've realized how easy it is to burn your sugar, right? Sugar is a fairly low melting point, or at least decomposition point. But if you try to do the same thing with table salt, you can heat the hell out of table salt. You could crank the burner up to like 10, and your table salt's not going to turn into a liquid. It'll still be table salt. Now, if you add water, it'll dissolve, but that's not becoming a liquid. We're talking about just the table salt on its own melting. You have to heat table salt to a ridiculously high temperature, and that's because ionic bonding is very, very, very strong. Another feature of ionic compounds is that they tend to make cubes, or at least very flat surfaces. So you can see here, in my salt crystal, I have a cube, but also up here in the fool's gold, you can see that the faces are shown in a pretty regular way, right? There's a lot of flat square shapes going on here. And I could find so many of these. Here's another one. And the reason for this is because of how ions arrange themselves. They want to arrange themselves in a structure that looks like this. The reason being is that if every... Oops, I put the wrong symbol on there. The reason being is that if every ion is charged, that charge is going to attract the opposite charge into all of the possible positions around it. And so instead of putting a new charge over here, so here's my plus, if I put a minus on there, this minus is only going to be attracted to this one. But if I could put this minus in a spot, like say, next to more things, it'd be more likely to form there. And so instead of forming on corners and stuff like that, these ions tend to form in spots and then everything forms around them. And so you end up getting a very flat and regular arrangement of ions that ends up looking very cubic. And that's just because the places that ions want to go are next to as many other ions as possible. And the way that they do that is by not making weird jagged edges. They want everything to just be as lined up and straight as possible, to be as close to as many possible neighbors as they can. A good example of that is if you play with magnets. If you've played with like magnetic marbles or something, and you just like let them roll around, what they tend to do is they tend to clump up as close to each other as possible and not make like a long line. And the reason for that is because they want to attract to as many things as they can, because that attraction goes in all directions. Now, to form our ions, we need to get rid of electrons from one atom and add electrons to another atom. We're going to talk about that mechanism in more detail in the coming sections, probably next week. Actually, definitely next week, because we're going to stop after this. But if we can get our ions to be in these states, then what will end up happening is that they will attract together, and this attractive force is what's known as the ionic bond. Remember that opposite charges attract to each other. Now, in our lattice that we showed here before, these charges actually go in all directions. So, if I have a positive charge here, it's going to go in all directions. And so that's why all of these ions are going to fill into these spaces around it. And you get this sort of cubic repeating pattern. So don't think of ionic bonds as just one-dimensional along one left and right. They also go up and down in the front to back, because this positive that, if I circle it, you can't see that. This positive that this ion is seeing, wow, that didn't work. There we go. This positive that this is seeing also would attract in other directions too, and so other ions would come in and form an attraction and also make an ionic bond. Now, covalent compounds have very different properties. We're going to talk about covalent compounds in Chapter 5, but here's just a very brief overview. What a covalent compound tries to do is, instead of transferring electrons from one atom to another, they instead pool the electrons together and share them. Now, as a result, the direction where the electrons are pooled is always between atoms. So, for instance, if I were to draw water, the electrons that are shared are in these locations where there are lines, but not anywhere else. So the attractive force is only along these lines. What that means is that molecules exist independently of one another if they are covalent. And so these right here are molecules. Now, because they're molecules and they don't interact with each other, they don't stick to each other as well. And the result of that is that their melting points are much lower. This is why sugar can be heated up on the stove and it starts to decompose really quickly, as opposed to table salt. They look pretty similar in terms of their visual appearance. A sugar crystal and a salt crystal both, they look like little tiny cubes, right? But sugar, it turns out, is very different. All the sugar molecules are independent of one another, and they are not bonded together in some sort of giant lattice. Whereas with the sodium chloride in the table salt example, they did form one giant lattice. And if you want to break that apart, you have to tear them all apart. Sugar, it's not as hard. All right. And again, we're going to talk about how covalent bonding works in more detail in the next chapter. And I think that's it. I think that's all I got. I'm not going to start a new chapter with just 3 minutes left. So we're going to put the little bookmark here. And we're going to call it a day. So back to the title card for us. What do we have left to mention? So quiz number 3 is going to go online. That's going to be due. We'll put that right here. I'm going to overtype some stuff here, unfortunately. Quiz number 3 due Wednesday, which would be the 28th. So, yeah, extra assignments are going to start stacking up as we move through the quarter, okay? So don't get overwhelmed. You have a whole weekend. Lab worksheet number 1's due tonight, so just that's got to get off your plate. Do quiz number 2 soon, and then do quiz number 3 after that, and don't let things pile up, okay? And you'll manage. You'll be okay. I do want to thank everybody for coming out to the lecture. I hope that you will send me any questions over email or chat on the Discord. Make sure to use those services because they are there for your use. And then finally, have a wonderful weekend. I may be unavailable this weekend because I'm getting my second COVID shot tomorrow. Fingers crossed I do okay. See you next week.